Now we're going to kick this thing up a little bit. This time we've got a 15-minute slot with 2 speakers on stage. So I'll ask Steve Stoyanac of Chillicothe Metal Co Corporation and Robert Simmons of Seismic Source International to come to the stage. These gentlemen are going to double team the final 15-minute speaker slot with a brief presentation that gets to the heart of the International Building Code. Robert and Steve have been EGSA members for many years. Steve was our 2004 EGSA president, and Robert is an officer of the Codes and Standards Committee. Welcome to the stage, Steve and Robert. I'll let you guys have it.
Great.
All right,
Thanks,
thank you.
Go ahead, Steve.
Okay, good morning, everyone. Thank you. We will be brief here. We're a little bit behind. In the next 15 minutes, Robert and I would like to share with you an overview of the International Building Code and just go through the ABCs of compliance, maybe share with you a little bit of history and share with you what impact this code has on our industry and the products that we all serve it with. So what we want to do first is make you aware of the risks. We want to talk a little bit about the requirements of the building code. What exactly do we have to do to be compliant in a credible manner? And then we want everyone to commit to do it right. Interestingly, this is not a new code. This code is now 17 years old, if you can believe that. The first version of the code was released in 2000. I believe we're in the 5th revision of the code.
It is.
The code
yes,
is by
right.
mandate, it has to be revised every 3 years, but it's been around and there's still some ambiguity and some misunderstanding about the code, so maybe we can clear a little bit of that up today. First off, let's be aware that earthquakes are real. They happen, they're destructive, they're violent, and we have to supply products into this arena that will make it through an event and perform and keep buildings alive after an event. Just a little video. I think many of you might remember this.
Visibility was 8
event.
miles, and the temperature around the Bay Area was 75 degrees.
27 years, a World Series game will be played in Candlestick Park, the Battle of the Bay. They had second base, so the Oakland A's take a lot of evidence.
Second, please.
With video cameras everywhere, this was the most visible earthquake ever.
Dark, and then the generators caught, and so we had partial light.
Again, as we take a look at that, that appears to be what would be the Marina District, the entire upper deck of the Cypress.
People were largely without power in some of the areas that were badly hit, even in areas where the power was.
The entire city, at least the part of the city that I have been in all day, is completely blacked out. There are no traffic lights.
Probably been talking to viewers about.
On the drive-in, I wonder what that drive-in was like.
It's very dark out there because a lot of electricity has been lost around Southern California. Good morning.
That picture right there is taken from the Washington Monument. There was an earthquake here several years ago in West Virginia, and that was from a camera mounted inside the monument. But that earthquake was in Virginia, fell all the way up to as far north as Nova Scotia. This little video just shows some significant earthquake activity in the United States. So again, we want to all be aware that earthquakes are real. They happen, and they've happened in the past, and they'll certainly happen in the future. This map here of the United States depicts seismic activity, and we tend to sometimes think of earthquakes as a California problem. It's not just a California problem. It's sometime or another, all 50 states have experienced seismic events. Certainly more in some states than others, but it's across the country, coast to coast. Okay, let's be aware of the effect on our equipment. Again, earthquakes are violent, and we can simulate this with shake table testing, and this video will show you some of the violent loads that are placed on our equipment. Okay, so in the best interest of time, we are going to move on, but the point of that last video is if you're in a building and there's an earthquake, stay away from the copy machine because it will track you down and it will get you. Okay, so what happened? There were two significant earthquakes, 1989, another one in California in 1994. The cost of those two earthquakes was around $100 billion, and a significant amount of that cost was attributed to failure of non-structural components, the things that we supply. So by congressional action, they went to FEMA, and FEMA created this new organization we call NERP, or the National Earthquake Hazard Reduction Program, and it was out of that group of several governmental agencies that we received the International Building Code, and again, that was released in 2000. And that's a comprehensive building code. It addresses structural, but also non-structural, and that is seismic design for non-structural components, and that's what we all deal with. So FEMA, once this code was released, FEMA went out to all 50 states and said, we have this code, and we want you to adopt the code, and if you do not, you may not be eligible for emergency funding should a catastrophic event take place in your state. Of course, overnight, all 50 states adopted this code. So it is law. All 50 states have adopted this through their legislative process. It's law. It's not going away. It will be with us forever. But beyond that, it is a good code. It holds us accountable to build good equipment that will survive an earthquake and keep buildings alive and keep people safe. There is some liability for code violations. There is case precedent for people not meeting building codes. And I'll just comment real quick on that chart. That was a survey done amongst engineers, the engineering community, and you'll see of their concerns in the engineering community, top, most of all, is concerns around codes and standards, understanding them and staying on top of them. So as an industry, we have a responsibility to share this information with everyone, and especially the engineering community, because it kind of starts with them in writing good specs. Okay, this is just a snapshot of a chapter out of the code, and I certainly won't read it all to you, but it says there, each manufacturer of a designated seismic system, and emergency generators are almost always a designated seismic system. We have to test or analyze our equipment to make sure that it will survive the loads of an earthquake, and we need to submit a certificate of compliance, and we need to test our equipment. We need to certify it by testing on a shake table or by engineering analysis. And with that, I will turn this over to Robert, and he'll go into this in a little bit more detail.
Okay, thanks, Steve. It's beginning to feel like Vanna White back there. Should turn some ABCs over there. And looking at some of those videos, I think it's kind of humorous. Who's the first people running out of those buildings? You know, the teacher is in there teaching Spanish, and well, you're on your own, kids. I'm out of here. And then the security officer was, running like this. Ah! Earthquakes really are pretty scaring. I live in Houston. I tell people I have hurricanes and things like that, but I don't want to live in an earthquake. I just design for earthquakes. So what we're going to do is look at what the building code requires in order to design for earthquakes, to survive earthquakes. Okay, so we're going to look at where, when, and how to be able to design our type of products for earthquakes. We'll look at the where and the when here on this map. It's kind of easiest to look on here. It's nice, it's color-coded. If you're in one of the areas that's white, you don't have to worry about designing your equipment for earthquakes. I'm in the Houston area, nothing there. We just got hurricanes. But if you're in the kind of pink area there and you're in a building that's like a hospital, then you're required to design your equipment for earthquakes. If you're in the blue area and you're in something like a school or an assembly area or maybe a shelter, then you have to design it to survive the earthquake. If you're in the green area, you pretty much have to design it for any type of building that's going to survive an earthquake. The code puts that in a chart here. I kind of went over that. I'm not going to go over the chart too much. But most of the equipment we have has an importance factor of 1.5, which means it's in that right-hand column and it's going to be required. So if you're required to design it, how do you do that? And that can be broken down in pretty much 3 ways: analysis, shake table, or some combination thereof. Easiest thing to do is look at examples. Some examples there on the left are things that have to be shake table tested: generators, motor control, switchgear, fans, anything that's mechanical or driven or has electricity running through it, it has to be shake table tested. If it's dead, so to speak, like an enclosure in a tank, you can do an analysis. Some typical examples of analysis: an enclosure there shown on your left, a tank shown on your right there. Typical shake table: a generator mounted on a shake table there on the left, a controller mounted on one at the right there. And a typical combination comes in when you have items that are really too big or too custom to be shake table tested, and so you do analysis on things like the enclosure and all the guts that are inside that have electricity running through them. They have to be shake table tested. You combine those together and you get a legitimate certification of compliance to the seismic requirement. So we looked at the A, awareness, saw some videos, looked at the B, building code requirement. Now let's look at C, the commit to do it right, which I think is maybe the most important part, because like we said, the code has been around for 17 years, but is it really being done right? I'd argue it's getting there, but not there. The commit to do it right can be broken down to 3 principles: minimum code requirements, which we've looked at; industry standards, which we're going to look at as the link; and then credibility by accountability, and that's what the industry here does. So a reputation takes years to establish, but it can be lost one earthquake, one hurricane, and people go, hey, your product didn't do what it was supposed to do. So you're the authority of jurisdiction, and you're submitted a certificate of compliance that says this piece of equipment is going to survive an earthquake. Which one of these 2 certifications is a valid certification? Who thinks the one on the left is valid? Raise your hand if you think that's a good one. I redacted the people so that, protect the not so innocent. Who thinks the one on the right is credible? Well, the reality is they're neither one. I made them both up. And my father-in-law used to say, he writes books, I never saw paper that rejected ink. Bottom line is, it doesn't matter. And I've actually talked to authorities of jurisdiction and asked, how do you know? Well, he says, if it's on fancy paper, it must be good, right? Well, not really. And that's where the industry comes in. The industry creates international consensus standards that says, this is what companies have to do to be qualified to list. This is what companies have to do to be qualified to do testing. And they're audited annually, or sometimes more than that, to make sure that they're doing what they say they do and that they're able and qualified to do what they are with regard, in this case, to seismic certification. ISO consensus standards say what have to be done. 17020 and 17025 do those qualifications. That's why there's listing agencies. The second thing the industry does is it creates the standard, the method of test that must be required. So the building code kind of sets the playing field, and even some of the rules, but it doesn't really referee it. It doesn't police it. So if one person tests it one way, another person tests it another way, and they both say they're certified to meet seismic, well, how do you know who did it right? Industry standards create methods of test that you must follow in order to be able to be qualified. So when you follow these particular consensus standards, then you know test manufacturer A and test manufacturer B, they're compatible. So you can make an informed decision. If we could follow all of these kind of concepts of committing to do it right, you wind up with what's the code calls a label. It also is a certificate of compliance. The only difference between a label and certificate of compliance is something you submit. The label is something that you actually put on the piece of equipment. There's some bullet points there that are required to be on that label. The main things I want to point out are things that are traceable, things like serial numbers, listing and certification agency, test lab, public report. That's all really important because the reason that the system works is because you have credibility by accountability. You can look up online now and go look at a listing agency. If you want to look at Seismic Source International, you can look it up, see that IAS accredits that, be able to certify for Seismic, to list for Seismic. If someone says that they have a label and they have XYZ listing company on there, you can go to that company and say, hey, is this person actually listed? They do the test that they said they do? And then they should be able to give you a public report that you can get online also that says, hey, this is what they tested to, this is the test method they used so that you can actually check the credibility on it. And all of those systems are then audited annually so that if they, whatever they tested and manufactured in year one, 5 years later, you know that it's still good. So, we have a video here to show some of the credible tests and maybe not so credible. Well, I'll see if you can pick out which ones are good and which ones are not. 3, 2, 1. Shake it up. All right, you guys figure out which ones were good and which ones were not. You know, I will say that very last one where it's kind of, you know, looks like it's shaking, that was done at a university to try to meet the requirement for the seismic compliance, and it was completely no good. They thought, well, okay, we have this thing that goes back and forth, we'll put it on there, and okay, it's good for seismic. So sometimes it's obvious, sometimes it's not so obvious. That's why the industry creates the test methods and the credibility behind it. So when you follow that, you know that the label is good, and then you know that it's certified, and you know that you have some confidence that it's going to operate when the event happens, and you can rest on that. And that's what authorities of jurisdictions and engineers are looking for.
Okay, just a couple quick comments to wrap things up here, folks. EGSA has published a working best practice to help any of you work through the IBC certification process. We also have a lot of EGSA members that have been through the process with their products, and Robert and I are available. If anyone has any questions later on, please feel free to get with us. We'll help you in any way we can. But again, this building code is not going away. So I think it's just a matter of time before we all have to step up. But I think it would be really good for our industry to really embrace this and really do it correctly and in a very credible manner. So give us a shout if you need help with that. I will let Robert finish this out with just a comment on his hometown.
Yeah, I kind of added a personal note here. This is where I grew up. I'm 53 years old now, so I've lived in Houston my whole life, and I've seen just about every kind of storm, every kind of hurricane come through. Felt like I'd seen everything. When Harvey was coming in, I'm like, yeah, okay, I've been there, done that. I'm high and dry. Well, 2 days later, that's our city. That was a 1 in 40,000 year flood. The codes that we've gone through, those are about a 1 in 2,500 year, so never say never. As an engineer, as a PE, I'm required to protect the public. our organization here is required to not be complacent, but instead plan instead of react. So that's the one thing I want to leave you with. Thank you.
Thank you.